MIT 仿生机器人实验室总监Sangbae。
你好. Hi everyone. Good morning everyone. It's a great pleasure and honor to be here. I really thank the organizer having me here. I'm an associate professor in mechanical engineering at MIT, and I'm specializing in designing a robot. But I'm specialized in design, so I'm going to talk about how to design a robot for the future. So this is one of my creations. This is my probably the most recent creation, and I'm going to talk about mobility of the future. So before we're talking about the technology, let's talk about the current technology. This is amazing. Everyone, almost every one of you probably have this and then use it almost every minute or every hour, right? It's amazing technology. We use this to gather information or send the information. So that really changed our lives. It's all about information. It doesn't need to move. It doesn't need to touch me or push me or generate power, right? But this is the current technology. It's going to go down. I think we're going to move to next issues. We will move to the physical interaction. So information is not enough. We probably need to have in physical interaction to delivery and elderly care. You know that the population is shrinking in the younger generation and then increasing in the older generation. We're going to have a lack of literally a physical help. And then we don't have don't have enough people to help these elderly generations. And companionship. This cannot be just companionship if you don't have a physical interaction. You need to be able to move around and then chase you, say hi to you. And home security, you need to be able to move around to do this. And all these new technology that really can help us our life, and then the next level, we need the mobility. You walk around all the time, you don't appreciate it, but it's actually a very hard problem. So think about mobility. We already invent the cars, we invent the bicycles, we already use wheels all the time. It's very easy to use. But if you look at what animal can do with the leg, it's just incredible. PR2 is one of the pretty exciting robot. But in order to move stably, the base should be really wide. How much space do I need? I need only 20 centimeter by 30 centimeter, and then I can move around. Have you seen flight attendants working in this small compartment? One person going in and one person going down. We need a very small space, and we can do almost everything just because we have a leg. I think in order to have a robot in our space, in your home, or even a street, I think legged locomotion, legged mobility is going to be the future. Think about this situation.
It was the accident at Tokyo Electric Power Company's Fukushima Daiichi nuclear plant. The damaged reactors released radioactive substances, making it difficult for humans to deal with the crisis. People needed something that could confront the dangers and bring the plant under control.
Think about sending a wheeled machine here. You can't really navigate in that narrow environment. And this is the extreme case, but your house might not be that different. The laundry is everywhere, your toys around, your wide-based wheel system cannot really function there. So that's why we need to really learn from animals. So this is centering basically my research. We try to really learn from animal to design a locomotion machine that can actually move around freely like us, like you. The problem is we cannot just copy nature as it is. Even though animal does amazing thing, cheetah runs like 70 miles per hour without even blinking their eyes, and they can climb in the mountains without falling. But their design is for surviving in the nature. Our purpose of designing a robot is slightly different, right? We can design for elderly care. We design a robot for disaster response. And there are other problems as well. There are animals are using muscles. Animals use their brain. We have a different component. We have different building blocks. We have motors. We use the electric motors. We use our computers to really mimic the function of our brain, and we don't really know how our brain works. I have absolutely no idea how can I speak to you and watching your eyes and moving my arms without falling apart? So it's very incredible things we need to learn. So focus is we need to really learn how to extract the principle. Instead of copying every single features, we need to understand what's the principle of running. So we need to focus on the function, the principle of function, and then we have to recreate in the engineering domain. Let's talk about robots. So we talk about robot that moves around. This is probably the state-of-art robot technology. It's incredible. It actually exceeds humans' capability in some sense. It's more precise, more repeatable, it's stronger. Basically increase the productivity in the order of magnitude or more. And you can see things like lifting entire car chassis without having any error. So it will show in a minute, like look at this like a car chassis coming out of this window. Imagine like 4 people, 5 people holding this heavy chassis and then, oh, push left, push right, and then it's gonna be much worse than a robot. Robot can do really well. The point is, they don't do any dynamic physical interaction. They are the machine that just move exactly repeatedly as we told. They move just as a position control. They don't actually physically interact with me. They are too dangerous. They are too heavy. They are too rigid. All these amazing tasks that robot does, they're just feeding their position from the lookup table. They don't actually interact. They don't really intelligently interact like we do, like shaking hands and tapping on the shoulder or massaging it. All these physical interaction is missing. And I will tell you why that's the case. They're not compliant. So we had this amazing competition in last year, June. But the robots their intelligence is amazing, but their machines are not designed to be able to interact with the environment. They're not compliant. I can jump, right? I can land without having braking. These robots are so rigid, it cannot really safely interact with the environment. So we have a lot to do to develop the function in the brain, but their physical design is not ready to really safely moving around. So like look at this robot, particular robot. It just falls exactly as it shapes. It's like a sculpture. Because they are using the technology we use in the manufacturing world. And then they're really rigid, they're only focusing on the position control. It's really hard to imagine like a human pushing something arm and then fall apart because we're very compliant, and then we're very dynamic. Even though I'm moving like a few meters from here to here, I'm always in dynamic. But all these robots are actually very rigid. So think about it. If you move out of any door, any building, the door is springed, right? And then if you try to open the door with the rigid scheme, you can't actually really push because you're going to fall backward. How we open the door, we actually use our dynamic force because we're dynamically balancing. So that's what we're really trying to do rather than just quasi-static. So if you look at the current robot technology, they just boils down to 2 categories. One is manufacturing robot, which is very rigid, and then it's not very efficient, and it's not really even powerful. Or construction technology, which is heavily used by Boston Dynamics and other companies. And they can actually interact with the environment robustly. They don't break. But they are really inefficient. I'm going to talk about that later slide. And then hydraulics, yuya, probably in Chinese. And those are very heavy and expensive. So, and then once you break, it's a lot of problems. So I think we need to have a different paradigm. We need to really have a paradigm shift from manufacturing or construction technology to new type of robotic technology, not only software-wise, even in the hardware. So that's why I've been working on this MIT Cheetah technology. It's specifically designed for interacting with the environment. As you can see, running involves impact. It's very, very dynamic and very capable. It's faster than me. It's still not using the full power yet. It's a very powerful machine, and at the same time, it doesn't break when it hit the ground. You can run outside, it can turn, and it has a sensor in front, so it can actually detect the obstacle So the sensor is in front of the robot, and then it can detect. Sorry, I think I missed. I need to go back. Just one more time. Try one more time. All right, I will just repeat one more time because I missed the last bit. So it has a head, but doesn't have it has actually a very simple sensor. It can run up to 22 kilometers per hour, so about as fast as me. And it's using purely electric motors, actually really powerful, and it is very efficient. It's as efficient as the animal at this point. It can run outside, it can can turn. And most importantly, it has the sensor in the front, and then it can detect the obstacle and then adjust the steps, and then it can jump over. And these things are all happening in the real time in the computer in the machine. And that's about the highest obstacle it can jump. It can actually jump about 1 meter high, but it doesn't know how to land. So that's the main problem. So we'll keep on working on it. So this is very different technology. We can actually handle impact. The robot can be very compliant, and anytime you want. It can be like a damper, like in the car. You can be rigid as well, but at the same time, you can be very flexible. It's more like an animal, more like a human. So that's actually very, very important to have in your robotic machine, so you can freely move around and then safely interact with the human. So now it's about to be ready to serve a physical interaction beyond the information. If you look at animals, every step is an impact, and then they can handle it because they're compliant. You can probably distinguish how incredible the animals are compared to the machine we have at this point. This is like a 60-degree slope. They're running around without having any problem because they're built for interacting, built for physical interaction. Let's talk about efficiency. I talk about the hydraulic machines are not very efficient, and then electric machines current electric machines are not efficient either. This metric is the cost of transport. It's like an inverse of mileage. So lower number is more efficient. So human is actually very efficient. Human is about 0.3 when it runs. When you walk, about 0.2. It's actually a very efficient machine. If you look at electric machine, one of the best humanoid in the world, it's about 6 times worse in terms of energy efficiency. They spend about 6 times or 7 times energy to do the same thing, to move and walk around. And cheetah, I'm trying to catch up with the cheetah. Cheetah is about 0.4. Cheetah is also very efficient. And the hydraulic machines are about 30 or 40 times worse than animals. They consume about 40, 30 times more energy to do the same thing. Our electric cheetah, our MIT cheetah, is actually almost the same as the animal. So you already achieve efficiency of an animal, and we can be actually better than animal in the future.
Like animal,
So this is probably the first time in human history robot walked with a human in the street. This is MIT, and then it's a holiday season, so there's no MIT people, but there are there are few tourists, and then they just gathered in 3 minutes. It's not very common things to see in Cambridge. And we prepare for this walking algorithm for Bill Gates' visit. Bill Gates visited our lab 2 years ago, and then the people are really interested. And I thought they were going to be scared, but actually they're not. They're very friendly because the robot looks a little bit more like a dog. And I think this is going to happen pretty soon. So prepare for the era of the robot next to you. This is a slightly different project. We prepared this project.
Since 1980, an average of 107 firefighters
for
have
disaster
died
response.
in the line of duty
So listen.
in the United States. Thousands of workers die each year in mining accidents. And nearly 250,000 people are still displaced by the Fukushima nuclear meltdown. Gil Pratt, the program manager for the DARPA Robotics Challenge, has stated that if robots were able to take action within the first 24 hours after the cooling system malfunctioned, the first nuclear reactor could have been stabilized.
Here at MIT, our team is trying to fundamentally change how we tackle disaster situations in order to prevent these tragedies. Imagine we could send a robot in a disaster situation instead of risking more lives. Imagine this robot can bring all the capabilities and training of our first responders. This is our vision on how our robotic technology could make our world a better place.
In the last 2 years, we've been working on the Hermes humanoid system. Hermes is unique because it is designed to be highly dynamic. Powerful motors give it the strength to do heavy work. Light limbs allow fast movements. Flexible hands are robust and designed with the dexterity to use human tools. This is a robot we intend to send into dangerous situations. But Hermes is not alone. A remote operator controls the robot using a motion capture suit, which is custom designed to relay the body's movements in real time. It can allow control of the robot from a distance potentially up to 1 kilometer, while keeping the operator safe from danger. Above all, Hermes protects the life of the human responder. Hermes does what the operator does, harnessing the natural coordination abilities of the human. The operator sees what Hermes sees and feels what Hermes feels. We send the balance sensation of the robot back to the operator using the balance feedback interface. This feedback allows the robot to use the natural human balance reflex capabilities. In a disaster, more than surveying the situation, Hermes can do dynamic physical work. Hermes will learn to walk and run just like the MIT Cheetah robot. Merging the two technologies will allow the next generation of robots to surpass the capabilities of humans. We are working on the newest generation of disaster situation first responders. We are building Hermes to save lives.
He did that. He put that fire out.
Thank you for your attention. 谢谢。